Hey, North, Mr. Yergler here. This video is going to go into electrolysis and electrolytic cells, kind of opposite of the galvanic cell, where the chemistry is creating electric current. Here, we're using electric current to create the chemical reaction. This video will show you how to determine kind of what's being oxidized and what's being reduced in an electrolytic situation. You may remember that sodium, pure sodium solid, is really reactive, right? If you put sodium in water, it sparks and it kind of explodes, and it's super reactive with water. And so you may wonder, how is it that we have pure sodium solid, right? Where does it come from? Because if it's so reactive, wouldn't it have already reacted? And the answer is yes. So we have to produce it. We actually produce it through electrolysis from regular table salt. So this is molten NaCl. So not aqueous, not dissolved in water, even though it kind of looks like water in the picture. It's molten NaCl. So just regular table salt, you melt it down. It has to be at a really high temperature. And you run an electric current through it. You have an anode and a cathode. And at the cathode, we're reducing the sodium ions to pure sodium metal. Because it's at such a high temperature, it actually forms a liquid, and it's much less dense than the salt. And so it rises to the surface, and you can collect it that way. So in electrolysis, it's an unfavorable reaction, right? Sodium chloride never automatically splits into pure sodium and pure chlorine gas. Both of them are quite reactive, and so they are much lower in potential energy when they're together. But we can force them apart with electricity. Just like in a galvanic cell, the cathode does reduction and the anode does oxidation. This is also always happening in a single container. You don't need to have it in two separate containers. We do have a barrier in this situation because we don't want the two products of the reaction to mix and then reform the reactant. But it's really just one container because you are reducing one component of the solution and you're oxidizing the other component of the solution. This is a setup for how they actually do it in industry. This was developed by some chemical engineers in the 1920s. They have the anode in the center with like this kind of big collection ductwork to collect all the chlorine gas, and then they have the cathode in like a ring around it, covered by like an upside down trough. And that trough, because the sodium is less dense, it floats and then gets caught and then kind of funneled to this container where it can be collected and separated. So this is kind of a combination of electrolysis to create the products and then also a separation technique to keep them apart. Here's a slightly more complex situation. We can actually figure out everything that's happening in this picture if all we know is that we have water in our beaker here. So we have a galvanic cell, a battery, producing the current that's used in the electrolysis. So looking at the picture, what is in the two test tubes? Notice that one of them is twice the volume of the other gas. So this has to be the H2 because it's H2O, right? There's twice as much hydrogen as oxygen in water. So this has got to be our H2, and this has to be our O2. So the overall reaction is just two waters producing hydrogen and oxygen gas, but it's actually a lot more complex than that because we're not showing the electron transfer and the redox reaction. On this side, in order to create hydrogen from water, we have to be doing reduction because the oxidation state of the hydrogen here would be +1, so it would have to gain an electron to form neutral hydrogen. Similarly, over here, the oxidation state of the oxygen here would have to be -2, so it's going to be giving off electrons to form neutral oxygen, right? So we have reduction here, so this must be the cathode, and oxidation over here, so this has to be the anode. All right, now we can get even a little bit more complex. Now we have a solution of sodium iodide. So sodium iodide dissolved in water, and we're running an electric current through it. Let's think about what species are present in the solution. We have sodium ions, right, because it's ionized because it's a salt, it's dissolved. We also have water, of course, and then we also have iodide ions. So what would the sodium do? Would it get oxidized or reduced? It's going to get reduced because it has a positive charge, and then we would have this voltage. The water could also get reduced, right? We could add electrons to the water, and we learned in the previous example that when that happens, we're actually producing H2 gas. The voltage here, this is coming from the standard reduction potential sheet, would be -0.83 volts. And then the iodide, would it be oxidized or reduced? It would have to be getting oxidized, right? Because it has a minus charge, it's going to lose an electron. Actually, two iodide ions would lose an electron each to form I2 because it's diatomic. Is there anything else that could happen in here? The previous example showed water getting both reduced and oxidized. Water's kind of unique in that way. It can undergo both reduction and oxidation. So we can think of these as kind of like our options for reduction. If we pass a current through this system with all these species present, we have kind of two options for reduction, and we kind of have two options for oxidation as well. So which one is going to occur? Both of them or only one? Think about it in terms of what gives off electrons more easily. The electric potential of the oxidation of iodide is lower in magnitude. It's closer to zero than that of water. So if we pass a current through this, the iodide is going to give off the electron before the water will give off electrons. And so that's what we end up seeing right here. This is actually liquid iodine, diatomic elemental iodine, coming off of this electrode. Similarly over here, the one that has the lower electric potential is going to be the half reaction that occurs. The presence of this OH, so it's a base, right? We're forming a basic solution. That's what's leading to this pink color, because a phenolphthalein has been added. So the acid-base indicator shows the presence of the basic solution. So this leads us into electroplating. Electroplating is kind of the application of electrolysis. You can take a gold anode, for example. You can oxidize it into gold ions and then re-reduce it onto a different cathode. And if you have that cathode be an object that you want covered in gold, then it gets plated with gold. And you could technically, theoretically, plate just about anything in gold. The options are practically limitless. So in electroplating, a thin layer, very thin layer of an expensive metal is typically reduced onto a much less expensive metal. So picture a situation where you want to electroplate your phone case to coat your phone in gold, right? In order to keep costs down, you don't want it to electroplate too much because the gold is expensive. So we have a 10 amp electroplating bath, and we want to plate it with 1.5 grams of gold. So we figured out that 1.5 grams is the amount that's going to give us a good thickness. Well, 1 amp is a coulomb per second, and this is the equation to kind of represent this. So I is used to indicate current, or amps. Q is the variable used for coulombs, and then time is in seconds, right? This equation is on your formula sheet. Remember that Q isn't the number of electrons. Q is the charge, a number of coulombs. And a mole of coulombs is Faraday's constant. Remember that Faraday's constant is 96,500 coulombs per mole of electrons. So if we have a mole of electrons, it's going to have that many coulombs of charge. So let's do some dimensional analysis. It's much easier to start with the mass. So if we go from mass to moles of gold, notice in our picture here and in our half reaction tells us that we're giving off 3 electrons, or to reduce it, we're requiring 3 electrons for every atom of gold. So 3 moles of electrons is going to be involved to plate 1 mole of gold. Times our Faraday's constant, and then divide by our amperage, because 10 amps is 10 coulombs per second, right? So I'm basically just using this as a conversion factor. That's really all it is. It's just another conversion factor that you can use in dimensional analysis. Multiply all that out, and you would want to keep your phone case in the bath for 220 seconds. And that would end up giving you 1.5 grams of gold. So that's electroplating and electrolysis. If you have any questions, as always, write those down. This is Mr. Yergler, signing out.